Okay, thank you. Thank you everyone for coming to my talk. It's with great pleasure that today I will discuss the research that was conducted in collaboration with Professor Gabriela Ochoa. And the title of this research is A Neat Visualization of Neuroevolution Trajectories. This research brings together two main techniques. The first one being NEAT, which stands for Neuroevolution of Augmenting Topologies. It's an evolutionary algorithm that evolves a population of neural network, and it evolves both the weights and the configuration, so in the topologies of the networks. So this has been introduced in 2002 and has been effective and adaptable for solving reinforcement learning tasks. It has been used in music composition, it's been used in biochemistry, as trading signal for financial market, and also geosciences. So the algorithm does this by using historical marking. So it marks its genes historically. It takes the population and it divides it into different species. It begins with minimal configurations, and then it grows to more complex structures. One of the interesting part is this control crossover, which is aided by this historical marking, so this innovation numbers. As you can see from the image, which is derived from the original paper, a genome is comprised of node genes, which can be either input, hidden, or output sensors. And then we have connection genes, which establish where the connection starts and where does it end in terms of nodes. The connection genes have got weights, and they are either enabled or disabled. And as you can see, there's also an innovation number, which is this parameter that helps to identify each gene throughout the evolution. The other technique is search trajectory network, STNs, and it's a fairly recent and innovative visualization modeling techniques that generate network which are comprised of states in the search space. These trajectories, which are node edge, are there to depict the optimization process of the algorithm. A node is defined as the best location of the search process, which is, in this case, will be the best solution of the population. And edges will be directed connecting two consecutive locations. An STN, therefore, is defined as a directed graph, which is comprised of nodes, edges, as described above. In the image, which is derived from the original STN's paper, this is an example where we have two algorithms that have been merged together. The yellow nodes are the starting point, and then from the starting point, these the evolution starts, and it depicts its trajectory. If you see, there are larger nodes, larger gray nodes that are the location where the solution is shared. The large dark gray one is the endpoint, and the red one signifies the global optimum in this particular case. So the research question is derived from both of these techniques. So first of all, in NEAT, we wanted to establish whether this recombination operator, this crossover, does truly provide improved performance when activated. On the other hand, with STNs, we also wanted to understand whether this technique could also be transferred to other systems like dynamic systems such as NEAT, and if it could help us understand how the evolutionary optimization process worked in terms of performance. So the reason behind these is because NEAT and algorithms similar to NEAT have been criticized because they it has been said that crossover does not add additional, it's limited, it does not add additional performance. So NEAT stands to prove that with this clever crossover technique, we can actually incorporate both parents' representation in the offspring, or the best part of both parents' representation. STNs, as I've said, is a fairly recent technique, which is not been yet applied to algorithms where the vector of solution is dynamic, so changes over generations. We identified a mapping technique to achieve this, which is using pickle dumps, which is from the pickle library, is basically serialization, which converts the neural network. So it converts the neural network representation derived from the genome into this byte string, that therefore this byte string can then be used as the signature to create these nodes in this search trajectory network model. So the method that we've utilized, so we started off by executing 20 runs of the NEAT, solving XOR and double pole balancing. These were both domain were used in the original NEAT paper, and the XOR is our classic classification of outputs, and the double pole balancing with velocity is basically a control task where the agent has to apply a force to a cart, which is bounded within a range, and it has to maintain two poles of different length in balance for a given number of time frames. It does this by receiving inputs such as the angles and the velocity of the poles. The next step was to average these results and then analyze them statistically using the Mann-Whitney test, looking for significance between the two variants, and we used a significance level of 0.05. And then from these 20 runs, we extracted 5 seed-controlled runs of each variant, and we used these to generate these STN models using the Ringgold-Tilford tree layout. We didn't stop at the visual part, but we also extracted metrics from the network to then quantify, to do a more quantifiable analysis in between the variants. So here we can see the contour, the convergence plot for initially for this one for XOR. We have fitness scores on the y-axis and the generations on the x-axis. So XOR starts from 0 all the way to 100 generations. In terms of fitness threshold, the domain is deemed solved when it reaches a fitness threshold of 3.98. The red line is the average best fitness for the no recombination variant, and the blue dashed line instead is referred to the recombination variant. You can see that there is also test 1 and test 2. These is where these are the points where we sampled for statistical testing. So we started, we did one at midpoint throughout the generation, and then we did one at endpoint. Similarly, for double pole balancing with velocities, we have the same coloring scheme. So these depict the average best fitness for no recombination and recombination. The scale for the fitness scores are different, as it is a different domain. And also, if we look at the x-axis, there's the range is from 0 to 1,000. So our test 1 and test 2 now differ. They are 500 and 1,000 for midpoint and endpoint. This is so these criteria have been exactly the same as the original paper. So we've not changed anything from what they've been done in the original paper. The parameters. So if we look through violin plots, we look at the distribution of these values. So A refers to the number of evaluation that it takes to reach a solution. And we can see that in the crossover in blue, compared to the non-crossover in red, we have a higher distribution of values for crossover compared to non-crossover, meaning that there are more values reside in the lower range of evaluation, meaning that it takes less number of evaluation to reach fitness threshold. And for the fitness value, this is the quality of the solution, which is basically this part depicts the midpoint effectiveness, which was tested at 50 generation for XOR. As you can see, the values reside more higher for the no crossover, indicating that the quality of the solution is significantly high. The only point where we don't see significance is at endpoint effectiveness. If we look at now the statistical results for double pool balancing, we are witnessing similar results. Again, the spread for no crossover, the spread of values is narrower. It takes less evaluation to reach the fitness threshold, and the fitness values again are showing similar result as for XOR. In this scenario, we have a significance for all three components. All the three components. The only thing that differ here is obviously the scales in the fitness values. So if we look at the data behind this, again, just to clarify, we can witness that the number of evaluation that it takes for no crossover in XOR and in double pool balancing is less than the crossover variant. When we look at also the best fitness, it is marginally higher, and the success rate as well indicates that more run and end to reach the solution, the fitness threshold. And for instance, here it's a total 100% that reach the solution. So if then we move on to the STN results. So this, as we said, it's merged STN. So we have placed both variants in the same plot. The beginning of the trajectories are where the yellow nodes are. So these are, as we recall, they are 5 seed controlled run. So they all start from the same point, and then as the evolutionary process start, they spread in between the two variants. The no crossover is in red, the crossover is in blue, and the gray nodes, as we've explained in the beginning, is the points where there is the solution are similar. So we have more, trajectories, more incoming trajectories in certain solutions, which may be which are similar solutions for other variants. So we can witness, for instance, in the initial stages of the evolutionary process that there is a lot of interaction between these trajectories, because as I said in the beginning, the genomes begin in a simple, and then they complexify over time. So there is a higher chance that the solution are likely to be similar in the beginning of the evolutionary state. But one of the interesting part of this is that we are able to witness, thanks to this tree layout, that the trajectories are shorter. Okay, so we visually were able to see that red trajectories are shorter, so the no crossover seem to have a simpler process to reach fitness threshold. Different from the graph that I showed at the beginning of the presentation. We don't see any global optimum here, because, and we only see dark gray solutions. So these are the solutions that actually reached fitness threshold, because there are many different configurations that may reach the fitness threshold. There is not such a one single point that where there is convergence to a one single optimal solution. So therefore, you're not witnessing any red dot in this representation. We did not just stop at the just like visualizing this. We wanted to move forward to confirm. So as I mentioned in our method, we decided to extract the metrics that are related to this STN, the STN model that you see. And we were able to confirm the results that there are less nodes, less edges than the crossover variant, and therefore the path length are shorter on average. This is for XOR. We then moved on to test for double pole balancing. And as you can see here, much clearer, we start from the same location because they're seed controlled. We start from the same location, and then the evolutionary process starts, and it splits into the two variant. This appears to be a much tidier looking plot because there seems to be less interaction, although there are points of attraction, still points that are shared between other variants and other trajectories. But here, even more, you can see that the length of these trajectories are indeed shorter than the crossover variant. You might think that these lines look different, but if we do a close-up, these are actually nodes that are squished together, so you are not able to see the actual trajectory in between these because of the data points. So as you recall, we had 1,000 generation for double pole balancing, so we have therefore more data point than XOR. So in order to fit in this representation, we had to shorten the trajectory length, and therefore you don't see them as much. Yeah, so once again, we didn't just rely on the visual aspect. We looked at the metrics behind this network, and we were able to see, once again, less nodes, less edges, and therefore path length being shorter. This suggested to us that it was in essence as if the crossover was kind of leading the search astray. So it was adding, in a way, complexity rather than simplifying. For instance, if you see here, these two comparisons, there's a clear, striking difference of how much simpler the no crossover process can be. So to conclude, we applied STN modeling technique because we wanted to better assess the performance of NEAT from a visual perspective, but also quantitative perspective. And also we wanted to understand the feasibility of this approach, whether it was possible. We statistically tested the crossover operator to understand if it does provide additional performance, and results have shown that there is a statistical significance, but it's in favor of the variant without the crossover. STN visualization did help to give us more perspective into the performance, so it helped to confirm these results. So we draw a conclusion that the recombination specific to the tested domains does appear to be just adding extra complexity, and it does not, and it's not found to be, it's not found to improve the performance, as trajectories are found to be longer on average. Thank you very much for your attention, and I'd like to take any questions you may have.
Thank you so much, Stefano. It's a very, very interesting, at least for me, it's very interesting work. So if you have any question, okay. In the chat, Emma asked the following question. One of the key aspects of NEAT is its use of speciation. Do you think the visualization could be modified to highlight the role that the speciation plays or not?
This is a very interesting question, and it's something I have not thought. There could be some aspects that could be extended in terms of visualization. So we are thinking for future work to add additional decorators to the visualization in order to enhance the information that we can derive from these models. We've not yet done so. We've not thought of it yet. But it is a very good point, actually, to understand, to better understand how the system does speciate the genomes throughout the evolutionary process. Is very interesting. No, and thanks for the suggestion. Yeah, I hope that answers your question. Please let me know if it didn't.
Okay, thank you. I would like to ask you a small question. Okay, Emma replies, also would be interesting to extend to your analysis to hyperNEAT, which involves CPPNs, as the dynamics are likely to be very different due to the relationship between genotype and phenotype.
Yes, that's one of the other aspect that we are considering to pursue, is to extend the same technique to other progressions of NEAT, which is involves also hyperNEAT. And the CPPNs, for instance, which is something interesting, how this indirect encoding actually works. We found, for instance, I've been working recently in a variant called adaptive hyperNEAT, which not only does indirect encoding based on spatial coordinates, but it also introduces presynaptic, postsynaptic, and weight of query connection to add the kind of to mimic the biological plasticity effect. So we're currently working on applying this to the next stage to identify how is this system performing with this extra plasticity component, because we have found that the process as it is seemed to be complex, seem to be taking long to evaluate, and because of the CPPM being constantly querying throughout the lifetime of the agent, it does require a lot of computation, and it's quite computationally expensive. So hopefully visualizing this will help to understand whether there are components that actually don't add any extra performance. They're just probably adding just accidental complexity, for instance. I hope that answers your question too.
Yeah, thank you. Another question in the chat or turning on your microphones? No? Well, I would like to ask you about other problems. Short and double pole balancing are quite simple problems. And the thing is, when have you tried to apply your proposal to other problems, maybe to other complex problems, and what kind of trajectories and such you could obtain?
That is a very, very good point, because it is actually part of what we want to we intend to do. So as you said, they are fairly trivial domains. So we do want to assess whether the recombination operator, for instance, does actually add performance when the domain becomes, more complex. The reason why we decide to go with these two specific is because we looked at the problem from the perspective of the original NEAT paper, and we just assessed it as it was. So we said, what did they use? They use XOR and they use double pole band. So let's exactly do the same thing, and let's find what happens for this initial two domains. But then, as we were doing it, we came up with the same reasoning. Like, okay, it does not add performance for these two domains, but maybe it does for when the domain is more complex and it requires extra features or extra let's say how can I say, like in innovation, for instance, as well, in neural network topologies and solutions as well. So yeah, definitely something that we really have to look into, that, because it's not just the case of saying, no, it doesn't work. It could be very likely that it works for other domains.
Yeah, for sure. Thank you so much, Stefano.